Sound check.
Okay. So, quick review again. I'll just do this verbally. Letters, those are your elements. So like quick review. If I were to give you something like this, let's just do a quick example. Let's say that I gave you an unknown element. Let's say it was number 9. Let's say up here there was the number 17, and I told you that this was -1. Do you know what that stuff means? Like, or is that just like, oh, no, I don't. Like, could you tell me who X is? Right off the bat? Like, who is X going to be? I didn't actually use the right letter. Which one? Did you say fluorine with F? Or I think it's fluorine. I think fluorine is number 9. Chlorine 17. So hopefully you would know that due to this number 9 right here, that makes it F for fluorine. What if I asked you how many neutrons this thing had? How many neutrons does this have? Here. It has 8, yeah. Why? Well, there's 9 protons, and if we add 8 neutrons, that adds up to 17. What charge does it have? Well, the charge is -1. So how many electrons does it have? What was that? How many electrons? Oh, okay. How many electrons would it have if it has a -1 charge? 10. Right? Because there are 9 protons, but you'd have to have an extra electron to have a negative charge, so it'd have 10 electrons. Right? So hopefully that's a skill you possess. If you don't, we need to work on that. It's okay to make mistakes, but you got to grow from them, right? Don't make the same mistakes over and over and over again. Okay. So I have a job to help. Ooh, what did I just do? Undo that. I need to erase that. Okay, so that's some stuff with compounds. Like, for example, if I gave you CaCl2, could you name it? That's calcium chloride. If I gave you N2O4, could you name it? Dinitrogen tetraoxide. Different naming scheme, though, right? We use a different name scheme. What if I gave you AuCl3? Close. It's not gold chloride. It's gold Roman numeral 3 chloride. And that's sneaky. The reason why I need the Roman numeral 3 is that gold can either have a +1 charge or a +3 charge, and this must have the +3 charge if there's 3 chlorines. Okay. Maybe I give you something like this. What if it was Na2SO3? That's a polyatomic. Sodium sulf something. We just need to know the ending. That SO3, is it a sulfate, a sulfite? And you have a table you can look at, by the way, right? Don't forget to look it up. SO3 is a sulfite, so this would have been sodium sulfite. Or if I gave you H2SO3, well, now this is an acid. This would have been sulfurous acid. Okay, so again, if anything I just said in the last 2 minutes here is like, yeah, I didn't know that one. Ask, right? That's how we learn. It's okay to make mistakes, but we got to grow. Okay? So here's what we're focusing on now then. Now that we've put those letters together into words, we're working on types of reactions. And last day we focused very specifically on something called balancing equations. It would be where there's like coefficients. Like, well, let's do a real basic example. Let's say I gave you CH4 and we added some O2 to it, and we turned it into some H2O, and I'll have to just write this down below because I'm out of space, and some CO2. Hopefully you kind of know what all of these different individual substances is, including why this guy is not just O by itself. We talked yesterday briefly about certain allotropes. Oxygen always comes in groups of 2. Well, we need to put numbers in front because as we write this out, this is like CHHHH. This is OO. This is HHO. This is COO. And if I were to like count up what we have, yeah, there's 1 carbon here, there's 1 carbon there, that's fine. But we got some problems. There are 4 hydrogens here, there's only 2 there. Right? So we talked about how to fix this. Let's have 2 of these by writing it out a second time. Now there's 4 hydrogens and there's, that's not what I wanted, I want the highlighter. And 4 hydrogens. And look at the oxygens though. So there's 2 oxygens right here. What about on the other side of the equation? There's 2 plus 2 more, there's 4. That doesn't work. Ah, but I can fix that. What if I were just to add an extra one of these guys by putting a 2 there? Right? That's kind of like the 1 minute or less version of what we did last day. But the whole goal was to figure out what coefficients go in front to balance. Okay? Today, we're going to focus now on different types of sentences. Remember how I gave you the idea of like how this is like nouns. These are the things that are occurring. And this arrow right here refers to like the fact that they're changing, right? It's chemically different. Today we're going to learn about some properties of equations, and then we're going to learn about 5 main reaction types. And then our goal is to now start writing some of our own sentences. So if I can use my daughter as an analogy again, every day at the end of school, she's in grade 1. Her teacher makes her write in her agenda, and she has to like write 1 sentence a day. Like that's as far as she's learned how to do. She can write some words, but like it probably, I can't imagine how elementary teachers do this, but like it probably takes this teacher like half an hour for my daughter to like write 1 sentence. Like it's challenging, right? But that's where we're at right now. Is I need to be able to get you started and say, can you write an equation now? So, anyways, that's our goal. Let me start here. One of the things I need you guys to know is that all chemical reactions involve the flow of energy. It was on a slide we had yesterday. All chemical reactions either absorb energy or release energy. It either gives it off or it requires it. Every single one. Now, it may be a minuscule amount, so small that we don't really notice the difference. But like, here's a really classic example. Let's say I just light something on fire, right? This is releasing energy because heat is being like given off. Light is being, I don't know, expelled, if that makes sense, right? And so we have a name for that. We call that an exothermic reaction. And one of the most common ways that we remember that for some people is that X at the beginning of the word kind of refers to like how it exits. And this energy, this flame right here, is exiting the system. Heat's being given off. Really, anything that you burn does this. Okay. A really classic example is something called combustion. A combustion reaction is whenever you have oxygen reacting and something basically it blows up. Anybody drive here somehow this morning? You probably put gas in a vehicle. Maybe if you didn't drive, your parents did, or if you took a bus, right? This would be a component of gasoline, hexane. You take the hexane molecule. You need oxygen for fire to burn. If you guys didn't know that, right? If you want to put out a fire, just remove the oxygen source. Right? So take hexane and add some oxygen. And when you're done, it makes some carbon dioxide and some water vapor. But it also makes some energy. That energy is what propels your vehicle forward. Right? And hopefully now you guys are familiar with the idea of, I know why those numbers are there. These numbers in front are here to help balance it and make sure that it's, the same number on the beginning side as the end side. I haven't even used the right words yet. What do we call the first side? What's the chemical term for the starting stuff? Yeah, reactants. And for the stuff you finish with? Products. You guys remember that terminology? So, but if the products also come with energy, we call it exothermic, and combustion is a great example of one. Okay. Now, the opposite of that, though, would be an endothermic reaction. And these are reactions that absorb energy. They need energy to run. Classic example would be one of these cold pack compresses. Anybody ever like had to use one of those in a sports game or something like that, right? You need to like put ice on your knee. Perfect, you guys have used this. Okay. Well, you know what it's really doing? You know why you feel like it's cold? It's because it's sucking the heat out of your knee. That's actually how cold things work. Cold things are actually just lacking heat, and it actually kind of removes the heat from the system. Brief tangent here. There's no such thing as cold, actually. It sounds really weird to say, but there's no such thing as cold. There's a lack of heat. There's also no such thing as dark. Yeah, just means there's a lack of light. There's also no such thing as stupid. Just means you're lacking knowledge. That's all. I like to say those 3 together. There's no such thing as cold, though. Cold just means that there's no heat. You're just lacking the heat you need, right? There's no such thing as cold. Right? So when a cold compress that you put on your knee feels cold, you're not actually feeling cold. You know what you're feeling is the heat leaving your body to run the reaction in the cold press. Yeah. So we call those endothermic reactions. They absorb energy. And some people will remember this because the N at the beginning of the word means it needs to enter. This cold press needs heat to enter it, and it causes this chemical reaction to take place. Whereas an exothermic reaction gives out energy. So those are the 2 types of reactions that are kind of like broad terms that we'd have. Okay. Really, they're all based on this major concept. And maybe you've heard this one before, maybe not. It's called the law of conservation of energy. Have you ever heard this phrase before? I mean, basically the idea is that there's a certain amount of energy in the universe, and it can be converted from one form to another. You can have energy that's like solar energy or energy in a battery. That's potential energy. That's a type of stored energy. You can also have active energy, like the energy in a fire, or the energy that causes the windmill to turn, right? Like that's called kinetic energy, right? And the long story short is that those are the different types of energy we have, and they can basically be released or stored at various different times. And so if I were to go back to this picture here, or really anything that's lit on fire, there was stored energy in the bonds of, I don't know, whatever the fuel source there was, right? And as we burned that fuel source, it then released it. It went from being a stored energy to a kinetic energy. Sometimes we actually do the opposite. We take kinetic energy and we try to store it up and try to like harness it in a battery or a solar panel. So that's kind of what I'm mentioning on this slide right here is, I'll just read. I rarely read off my slides, but I think I should here. Burning wood seems to just create thermal energy. You guys know thermal energy, like heat, right? But does this break the law of conservation of energy? Do we just like magically get heat out of nowhere? Well, no. There's energy present in the bonds of all our reactants and products. So all the matter that we ever have has potential energy just locked inside those bonds. And as those bonds get broken and remade in a chemical reaction, it releases energy changes. Right? So this wood that's burning right here, as it burns and it basically disintegrates into ash, the breaking of those bonds releases the energy we need. So here's a summary slide of what we just talked about. Exothermic reactions means energy exits. And basically it means that you're releasing energy. This would be a scenario something gets warmer. This means something warms up because energy is being given away. But it's also possible that you need a lot of energy to make the reaction occur. This would make the reaction, well, this would make you feel colder because you have to like give your energy away. I'll put a little note here. The reason why you feel colder is because you are losing, how do you spell lose? Losing your energy. So you feel cold. You lose your energy, you feel cold, and then energy enters the system so that the reaction can run. That's endothermic. I don't believe that's previous content. Have you guys ever heard those words before, or was that new? You'd heard this before? Oh, okay, so it was old content. Okay, perfect. Let's move on then. Here's the main focal point of my lesson then. I now need to, just like my daughter has her teach her how to like write sentences, and it's hard at the beginning. It's one of the reasons why I wanted to put down all these quotes here, is that you're gonna make mistakes. It's okay to struggle with this a little bit. Okay, you need some practice, but our goal is to learn how to start to write some chemical equations by ourselves, not just have someone give you one, but have one by themselves. It's actually what we're gonna do in our activity tomorrow. Tomorrow we're actually gonna go to Janae's classroom, and I'm gonna do 8 chemical reactions. I'm gonna sometimes burn things, set them on fire. One of them should hopefully be getting colder. Things will smell or change colors. And I'm just going to tell you what we start with. I'm going to tell you I took this and added it to this. And what I need you guys to be able to do is make a prediction as to what it's going to turn into. And in order to do that, you need to know some generic reaction types. So here's the first one. It's called a formation reaction. And this occurs where you take 2 elements and they come together to make a compound. Here's a really classic example. It would be sulfur and oxygen making sulfur dioxide. So first we're going to try to make what I call a skeleton equation, and then we're going to balance it afterwards. So let's start with the skeleton equation. I need to know what sulfur is. What letter is sulfur? Perfect. But what does sulfur come in groups of? 8. Yeah, it was on a slide we had the other day there. Hopefully you wrote it down somewhere. Sulfur actually comes in groups of 8. Oh, wait, we need to do one more thing. This is like the punctuation of writing a sentence. I mean, again, same thing with my daughter learning to write a sentence. Sometimes she puts a couple letters backwards, like sure, her S's could be backwards, or she writes an R backwards. But her teacher is focusing on put a period at the end of a sentence. Remember the day she came home and she told me, Dad, every sentence has to end with a period. Right? That's like what this is right here. We need to know a state of matter. What state of matter is sulfur? How do we tell that? It's solid, actually. Yeah, on your periodic table, I know it's not in color, but your periodic table often uses colors to differentiate between the things that are like solid, liquids, and gases. And sulfur is one of the solid colored ones, if you can find where that info is on your table. So that's your punctuation. S8 comes in a solid. Now we need some oxygen. Well, the letter for oxygen is O. But the next question we have to ask ourselves, as we're learning to write this statement here, is how many oxygens do you have at a time? Good. So the silly analogy I gave yesterday is sometimes you go to Costco and you buy an 8-pack of toothbrushes because you buy them for like the whole year, right? Or you buy a package that has 2 of them. Some things come in groups of 2. Okay, next question, we need our punctuation now though. What state of matter does oxygen come in? Gas. Yeah, and again, we look at that on the table and hopefully there's a way that it kind of indicates to you solids, liquids, and gases. All right, the last thing, and this is where you really need to build on previous knowledge. Now we need to know what sulfur dioxide is. Okay, well, sulfur is 1s twice. Perfect. Last question, what state of matter is it? And sometimes you won't know for sure. Sometimes we have to just take an educated guess, but we should always put some punctuation. It's kind of like how you could end a sentence with a period, but like you could end with a question mark or an exclamation mark. So sometimes you just have to guess what you think the most likely thing is. But we learned about some properties. This thing right here is a covalent compound. In general, covalent compounds are liquids or gases. Okay, ionic things are solids. Okay, and we had that in some slides we had previously. So if you want to write that down, things that are covalent are probably going to either be a gas or a liquid. And if it's ionic, it's probably going to be solid, or it could actually be aqueous as well. Remember that one chart that had aqueous on it as well? So this thing's a covalent compound. It's probably going to be a gas. We've now started our equation. This is called a skeleton equation. The basics are there. And just like with my daughter, who's writing sentences for the first time, it's painful and challenging at first. But, like the bottom quote down there, growth is painful. It's okay. Don't worry about it. Make mistakes, try it, ask me for help. Because here's the last step we got to put together. This is like the culmination of all the skills we've learned. We also need to balance it. Hey, there's 2 oxygens here and 2 oxygens here. That's fantastic. But there are 8 sulfurs here and not 8 there. So I think, let me rewrite this out again just so that I can balance it below. Just going to save some room here. There's 8 here and there's not 8 here, right? So I can fix that by, well, let's just make 8 of these guys. What did that do, though? There's now 8. This is an S, by the way. That looks kind of like a 5, doesn't it? Let's make that an S. SO2. Okay, so now there's 8 sulfurs and 8 sulfurs over here, but now it totally buggered up oxygen, right? Okay, let's put an 8 in front of the oxygen, yeah, because 8 O2s, that's 16, just means you need to buy 8 2-packs of oxygen. And now we've written our first sentence. This is known as formation, and the reason why it fits the pattern of formation is that literally A and B came together, become AB. This guy and this guy came this one. Now I need to point out though, this generic format I have right here doesn't account for the fact that there could be and probably will be little numbers down in the bottom corners, as well as big coefficients in front. I can't tell you that it's always going to be 2 A2s and 3 B8s to form 4 A2 B6s or 7s, right? Like there will be numbers down there in the corner. These numbers that I put here are clearly wrong because they don't add up to the right amounts. But like in general, if I could kind of undo what I did there, here's what makes something formation. Something and something else merge together to make a compound. We call that formation. Let's try some more examples. This is one of those things where I think I need to do a bunch of examples first, and then we'll let you try it on your own. So here's kind of the opposite of that. This would be where you have decomposition. And just like the word might kind of imply from decomposition, you're taking something and you're breaking it into pieces. Like a compound turns into 2 individual elements. Here you have A and B, and it's turning into A by itself and B by itself, and they are splitting. Okay. Classic example, water getting turned into hydrogen and oxygen. So let's take it from the top here. First, we need a skeleton equation. What is water? Fantastic. We all knew that. State of matter for water? Well, probably liquid. And this is where sometimes you just have to take your best stab at things. Because if this was being done at minus 30, it would be solid. And if this was being done at like 140 degrees Celsius for some reason, then it would be a gas. So like, but use your best logic. Always put punctuation though. So this is a liquid. Okay. It then decomposes into hydrogen and oxygen. This would be wrong for two reasons. First of all, hydrogen, you can't find hydrogens in groups of ones. The store doesn't sell them in ones. It only sells them in packages of two. And same thing with oxygen. Yeah. And we should include their states of matter, which is gas. Punctuation. Okay. So now that I've got kind of the basics going here, the last step is I need to balance it. So I'm going to rewrite this down below now. And I'm probably not going to rewrite it afterwards here, because once you get the hang of it, you're just going to put the numbers directly in there. But I'll do like an extra one below. Our hydrogen right now is balanced, because there are two hydrogens over here, and there's two right there. But our oxygens are not, hey? Because there's one right here, and two over here. Now, I can't cut this in half, by the way. Right? I go to the store, I want one toothbrush, but it sells me a 2-pack. I'm sorry, you just have to buy the two. And one's useless. Right? You know what the better option is here? Let's just do two of these then. Which means you need two of those. And hopefully that's making sense. If not, it's fine. Just make sure I try to help. This is then decomposition because one item split up into two pieces. Any questions on that? Okay, let me try some more examples. Here's another type. This type of reaction, oh, by the way, I should point out the 5 reactions we learned today are not all of what we learn in chemistry, like for reactions. There are many more types of reactions than these 5. But kind of just like when my kid's learning how to read, you know how like I don't teach her like silent letters or how like pH means F, right? Those sort of weird little twists. We're kind of starting basic. So if you're wondering, Chris, I found this cool chemical reaction. Which of these 5 is it? There's more types than just these 5. Okay, we're just kind of starting with some real generic ones. So here's another really common one, though. It's called single replacement. And the name for it really makes sense. What we're going to have is something here and a compound. And we're going to have like a switcheroo, where these two things here, they're going to switch spots. Rather than this guy be the single one and this guy be in the compound, we're going to kick this guy out to be single, and the other one goes in a compound. The best analogy I've ever found for this is like maybe like a dance partner scenario where B and C are dancing, and A taps B on the shoulder and says, I would like to dance with her now instead. And they kind of like, they switch out kind of thing. I don't know. So you can even see this in the words here. You had magnesium by itself, and silver was with nitrate. But now silver is by itself, and magnesium gets to go with nitrate. Yeah. So basically nitrate stays there, and the magnesium silver switch spots. So let's give this a try. Start with magnesium. Magnesium's an element. What allotrope does magnesium come in? If it wasn't listed on that slide I had back in our notes the other day, it comes in 1s. And almost all metals come in 1s. Don't even write the 1, just go with it as just magnesium. And magnesium is solid. Then we need silver nitrate. Let's make it Ag. What's a nitrate? NO3, yeah. And they both have a +1 charge, so we're actually good to go there. Now, without any other information on this, we need to take a stab at a state of matter for this. In general, ionic things are solid. But do you guys recall that one table in our notes that had like columns where there was a whole bunch of things along the top here? And then one column was very soluble, which meant it was aqueous. And one column was slightly soluble, which meant it was solid. We need to use that table to figure out how we want to figure out Ag and NO3. So if you have your periodic table nearby, can you flip to that chart there? Find that chart that tells you whether things are aqueous or solid. Gabby, can I borrow yours just to show everybody? So guys, we're looking, if you can see here, we're looking for a table that looks like this guy right here. So you always want to have it handy as a reference. Absolutely, yeah. Yeah. Okay, so we need to find either silver or nitrate in a column somewhere. And I believe nitrate has a column somewhere. Doesn't like NO3 minus? Doesn't it have a column in that table? I'll look over your shoulder. Which one is it? It's the second column in. And you guys will notice that in the nitrate column, it literally says that everybody, all, fit here, and none fit in the bottom category. So now I know which state of matter it should be. Silver and nitrate would be aqueous in water. That's important to look up. Okay, that's the little fine details that are important. Do you guys see how this is really going to be the culmination of everything we've learned? That I gave you the other day, it really is true. We're going to need to really draw on all of your experience to be able to write a sentence in chemistry. It's Ag. Silver comes in packages of 1. And it's solid, because that's the state of matter for an element. Then we need magnesium nitrate. It requires some previous compound building skills. Magnesium is Mg, and NO3 is nitrate. But that's wrong. Why? Why is it not just MgNO3? Because of the charges, yeah. So this really draws on previous knowledge. Magnesium had a charge of +2, and nitrate had a charge of -1. Do they fit? No. We need to put the NO3 in brackets and have 2 of them just to make this like compound balance. I haven't even balanced the equation, but the compound itself wasn't balanced unless I do that. Which means that if you're not good at writing compounds, you're going to struggle going forward. Growth is challenging, it's tricky. If there's stuff that you're missing from the past, we've got to fix that. Otherwise, you're not going to be able to keep going. Okay, I'm out of room to write a state of matter here, so you just have to write it underneath. But magnesium and nitrate, isn't it going to be the exact same thing, right? Isn't nitrate aqueous with everything in the top category? So there we go. Now, if it's okay with you guys, I'm not going to actually bother to rewrite this whole thing again. I'm just going to throw the coefficients in front where I need to. So let's just kind of start somewhere. This 1 magnesium, and there's 1 magnesium. Fantastic, cool. 1 silver, 1 silver. Sometimes it's best to actually treat the nitrate all as one big thing. See how you have 1 nitrate right here, but there's 2 nitrates over here? Okay, well, let's put a 2 in front of this guy. Over here, and this nitrate right here, there's 2 of. But hey, that buggered something up, right? Now there's 2 silvers. Voila, we're done. Placement. What we're eventually going to try to get, kind of see what our goal is. I'll come back to the slide in a sec. Let me make sure everybody wrote it down. I'm going to hop ahead to our goal, our purpose behind this lesson, just so you kind of see where we're trying to take this. Okay. I would like to be able to get you guys to the point where I give you the start of what 2 things happen to be when you react. And you have to be able to predict what it's going to make and then balance the equation. That's kind of our goal, is for me not to tell you everything, but just to tell you what you begin with. Okay. Let's finish off our reaction types, though. So did everybody get what they needed off this slide here? We're good? Okay, let's try another one here. There's actually a second type of single replacement. In the first one right here, I flipped the metal around. And so you guys will notice that the magnesium and the silver, both metals, they switched places. But you can have single replacement where the non-metal flips around. Here's an example. We have chlorine and silver bromide turning into this should be bromine. This should be I-N-E. Bromine. And silver chloride. And if you guys can notice it, it's the second one that flips around. The silver stayed the same. So again, it's going to be slow at first. I'm sorry if I'm boring you. If you've got this already and you're like, Chris, I can go faster. I'm sorry. I want to take this nice and slow to begin with. Okay. So let's start off with chlorine. What is chlorine's symbol? Cl. But what does it come in groups of? Need a table. Comes in 2s? And its state of matter is a gas. Yeah. Then we need silver bromide. Well, silver is Ag, it's +1. And bromine is Br, and it's -1. It fits together just fantastically. But now we need to know whether this thing should be a solid or an aqueous. A booklet. And again, I'll kind of draw like where the top the bottom category is things that are solid. And I got to find a column that has either silver or bromine in it. So, let's see, do we have a table for bromine? Yeah, it's the one that comes with chlorine and iodide. And if you can find the table I'm referring to, lo and behold, silver actually was in the bottom category. So we better make it solid. Okay, then we then need to do bromine, which is Br. 2. Hopefully you wrote that down. State of matter for bromine. It's a liquid, actually. Yeah, it's one of the 2 really dark colored ones on your table. So bromine's a liquid. And then for the last bit, we need silver chloride. Got a +1 charge. Chlorine. Fit fantastic. Hey, wasn't that same row, the same one up there? It wasn't like the chlorine and bromine all in that same table again? So I'm pretty sure that this one's also solid. There's a lot of little details here, hey? Like, this got real. There's a lot of things happening at once that you need to be able to do. You need to be able to know what allotrope to use. You need to be able to write any compound I give you. You need to be able to use that table and figure out a state of matter. And we still haven't even finished yet. You still got to be able to balance this thing. So check this out. There's 2 chlorines right here. There's not over here. There's only 1. So let's put a big 2 in front of it. That means there's now 2 big chlorines. Okay, well now there's 2 silvers right here. There's only 1 right here. Let's put a 2 there. That'll make 2 silvers. Now there's 2 bromines right here. Hey, look, there's 2 bromines right here. I think everyone's balanced now. We're done. So there's a lot of micro skills that you need to have, right? You need to know your elements. You need to know how to write your compounds. You need to know that table that tells you what state of matter to use. And you have to be able to balance. If you keep going on in chemistry, we want this to become second nature. Like for Kinsey in grade 1, writing her first sentences are painful. But like you guys can write sentences now, and although maybe you're like, I don't want to, like you can do it fairly quickly, right? That's what we need to get you to the point of being able to do if you want to take Chem 20 and 30, is that we want this to become second nature so you can then do something with it. Okay, so I know it may be frustrating now, but we're growing, right? Here's another type of reaction. This one's our 4th one. This one's known as a double replacement. And so basically it's like a double swap. Rather than having like one guy swap one out, it's like take both out and remove them. You used to have A and B and C, and this guy will go with that one, and this one will go with that one. You're just doing the old switcheroo. Right? Look at the words here. Lead used to be with nitrate. Now lead's with iodide. Well, where'd the iodide come from? Well, sodium used to be with iodide. Well, now sodium went with nitrate. That makes sense? You see how like they all flipped around there? All right, let's take it from the top. Lead 2 nitrate. What's the 2 mean? It's the charge on the lead, right? So lead is Pb. It has a 2+ charge. Then we need nitrate. Nitrate is NO3. Do they fit? What's nitrate's charge? It's -1, yeah. So if lead's +2 and nitrate is -1, they don't fit. We're going to need to like double up our nitrates. I'm not talking about doubling up the whole molecule. I mean, in order to even make the molecule itself, we need 2 of them. This would be like when you go to Costco and like you're buying a multi-pack. In this package, you get 1 lead, 2 nitrogens, and 6 oxygens in this big like collective package of molecules. Okay, that table we talked about here, you need to have it like out almost always. going forward. So top category is aqueous, bottom category is solid. There's the category for nitrate. But didn't we do nitrates earlier? Wasn't it all in the aqueous and none in the solid? Do I have that memorized properly? Is that right? Let me just look at your table. Nitrate column. Yeah, it was all and none, right? So that means that this should be aqueous. Okay, next one. Let's do sodium iodide. Well, sodium is Na. Iodide is iodine, I. What are the charges, though? Sodium's +1, iodide is -1. Sweet, fantastic. Charge time. Find the column that has iodide in it. Where does sodium fit? I believe sodium is not, like there's a few exceptions down here at the bottom, but sodium's not with those exceptions. So it's aqueous. I'm going to kind of lack room, so because I don't think I can keep going this way, I'm just going to draw an arrow down here, and I'll write them like that, if that makes sense. So this is kind of save space. So that's what we started with. Now we need to turn it into lead-2 iodide. Well, we know lead is Pb, and iodide is I. However, do they fit as I make the molecule? Lead is +2, but wasn't iodide -1, right? So we're going to need to have a 2 of those to make that work. And in that iodide column we were just using, yeah, guess what? Lead is actually one of the ones down there at the bottom. Is it the lead 2+ version, though? It is. So since lead is in the bottom category, thank you for sharing, by the way, that makes it the solid version. And finally, sodium and nitrate. Sodium is Na. Nitrate is NO3. Charges. Na is +1. Nitrate is -1. Yeah, we're great. Fantastic, it fits. Last step, state of matter. Well, I still have it written up here, don't I? Wasn't nitrate aqueous with everything? This is a lot of work, eh? It is a lot of work. And it really, really, truly does build on everything we've done so far. Right. Last step, we got to balance this thing. Because you'll notice that, like, even right here, there's I here, but there's I2 here. That's not good. Yeah, let's put a 2 here. Now there's twice as many iodides. Now that fits. You know what that did, though? That screwed up my sodium. Now there's 2 sodiums, and there's only 1 sodium right here. So let's put a 2 there. Okay, well, that screwed up my nitrates, right? Because now there's 2 sodiums to 2 sodiums, but now there's 2 nitrates. Just think of the NO3 as one big thing. This NO3, there's 2 of. Hey, look over here. This NO3, there were 2 of. Fantastic. And I think the only thing I haven't checked now is lead. There's 1 lead and 1 lead. Now we've written ourselves our equation. If this feels daunting, don't freak out, right? That's why I threw all these quotes on the board. You don't learn to walk by following rules. You learn by doing and falling over. I need you guys to try this, make mistakes, and get feedback, ask for help. Okay, let me try one more example with you guys. And then I want to give you guys some chance to try this on your own a little bit. Okay. So this is kind of my last slide like this. And then I have the idea of like predicting reactions. Okay. So this is the last like generic type of reaction we have. It's called hydrocarbon combustion. And I actually mentioned it earlier in our notes. This is basically where you blow something up. You light it on fire and it burns. And the reason why it's called hydrocarbon combustion is because you're starting with some sort of compound that has hydrogens and carbons. And the reason why we throw X and Y right here is that I don't know how many carbons and how many hydrogens the molecule has. It could be, for example, CH4. That is methane. It is what your house probably uses if you have either a stove that runs on gas or your furnace runs on gas. It's probably methane. But it could be C3H8. If you have a barbecue outside, you're probably using propane, the big like white canisters you fill up. Maybe it's C4H10. That is butane. butane is most commonly found in lighters. So if any of you are a smoker, which you really shouldn't because it's bad for you, but that's my dad talking there, a lighter would use butane to light something on fire. I already did another one earlier today. This was hexane. That's 16? No, 14. That's hexane. That would be maybe a component in gasoline. Do you guys see how like the numbers of carbon and hydrogen can change? That's why I give you CXHY, because we don't know what they are. But it always follows the same pattern. It always requires oxygen to burn, and it always makes carbon dioxide and water vapor. So let's try our last example here. I'm just going to erase this out of the way. We're going to start with something called methane. Methane was one of those like common word ones that I needed you to memorize. Remember how like we don't call it dihydrogen monoxide? We call it water. Methane is one of those common name ones. So hopefully you wrote it down somewhere, but methane is CH4. Now we need to figure out a state of matter, and sometimes it's a bit tricky, but I think we can probably is a covalent compound. Covalent compounds are either liquids or gases. But I kind of already described this one to you. This would be like the gas that you. So this one's a gas. If you had written down liquid, I'd probably still give you credit. Okay, because it could be a liquid if it was really cold out. Right? It's possible, right? What if it was minus 80 outside? I bet you methane would freeze. Right? Maybe it would. Maybe it needs to be minus 140. But like at some point it would freeze or turn into a liquid, right? So, but take your best stab at this one. Then oxygen. We've been here before. That's O2 gas. I'm going to speed this up a little bit. We're making carbon dioxide. You guys should know that one, CO2. And we all know the state of matter for carbon dioxide, right? Gas. And then it's going to make water. We got to think about this one for a bit. Water is normally a liquid. But when you blow something up and you combust it, it heats it up quite a bit, doesn't it? Right? Isn't that the point of blowing something up? Chances are it's going to be higher than 100 degrees Celsius when you combust it, right? When you have like your car running, you guys know how there's a tailpipe in the car? The tailpipe is to release excess gas. And sometimes water trickles out of the tailpipe if it's kind of cold, but most of the time this water will probably come out in a gas format. But if you put liquid, I wouldn't mark it as wrong. Like water can be a liquid state if it was cold enough out. So that one was actually a little bit nicer, wasn't it? Because I didn't even need to look up the table, right? That one table that gives you all the states of matter. Last step, we just need to balance it. And this is literally the one I did to start class, I think. I believe it was a 2 right here and a 2 right here to balance. And we're good. Okay. That's the knowledge part of my learning cycle. I've now shown you some stuff, and I hope I didn't freak you out, because this is one of the hardest days we have. If you could follow this and you're like, Chris, I got it, that's awesome. I'm actually thrilled. But if you don't, that's fine. We need to practice. We need to build this. Okay. So there's a couple ways I want to try to build these skills. One is the next activity. I got a couple slides on there where I want to start kind of letting you try things as opposed to me doing it all. Right? I need you to do some application and get me to give you feedback. Okay? And then 2, tomorrow we're going to do an activity where I'm going to do 8 different chemical reactions, and I'm going to tell you what I start with, and you've got to figure out what happened. And hopefully it'll be kind of fun because the fuel will blow up and change colors and do stuff like that. So let me do this last slide with you guys here. Let's do a little bit of the predicting part, and then I'll have you guys try the rest by yourself. Okay? So here's our goal. A chemist, a scientist, wants to be able to make predictions about what's going to occur. We should be able to figure out what is going to instinctively happen. This would be like Kinsey needing to finish the sentence off. Right? So I'm going to give you the start of the sentence. We got to figure out how it ends. Does that make sense, our goal here? This is one of the hardest things we do. So the first thing you got to figure out then is what kind of reaction is most likely to take place. Let's look at this first one right here. There's only one thing to begin with. Of the previous 5 equations we learned of, were any of them where you only started with just one item? This one doesn't start with just one item. This one doesn't start with one item. This one doesn't start with one. This one doesn't. Hey, this one did. Remember how decomposition started with just one thing and it split into pieces? That's what I expect this one here to be. So I'm just going to write above it a D for decomposition, just so I know what I'm working with, I need to break this into pieces. So one of the pieces I'm going to break it up into is just going to be lead. And the other piece I'm going to break it up into is bromine. Right? I'm literally, this is like Kinsey having Lego blocks, and I rip it apart. But I got to do a little bit better than this. That's not sufficient enough. First of all, this lead right here comes in groups of 1, and it should be a solid. But this bromine right here, bromine comes in groups of 2, and its state of matter on the periodic table is probably a liquid. One last step, it's not balanced, eh? Because there's 4 bromines right here, and this guy comes in packages of 2, so I better take 2 of them, so that 2 groups of 2 makes my 4. And this is what I'm going to try to have you guys be able to do. Does anybody have any questions on that one? Okay, let's try 4 more, and then I'll have you guys try some. This next equation, we got to figure out first, like, what type of equation do we think this is? Of the 5 we talked about, what fits best? So, like, let's look back through. Combustion? No, combustion involves carbon and hydrogen groups. I don't have that. What about double replacement, where you have a compound and a compound flipping spots? I think that's what we have, right? You have an AB and a CD. Here you have this guy and this guy, and this guy and this guy. They're going to flip spots and do a changearoo. So nickel is currently with nitrate. Let's put nickel with the SO3, right? Nickel was with the NO3. Let's put nickel with the SO3 now. And sodium was with the SO3. Let's put sodium now with the NO3. So that's kind of the basics I'm starting with. I just did the old flipperoo. This one and this one, they switch spots. I'm not even close to being done or even right at this point, by the way. There's a couple things I need to focus on. I haven't even looked at charges yet. What's the charge on sodium and nitrate? Sodium's +1. Nitrate's -1. Hey, that's convenient. Perfect. It's already good to go. Didn't we do this earlier? Wasn't nitrate like soluble with like everything? So we can call that guy aqueous. Sweet. What about the nickel sulfate? What charge does nickel have on your periodic table? Shoot. Ken just told me that nickel is either a +2 or a +3. I need to figure out which one to use. You know how I figure that out? I go back to the previous example right here and I figure out, well, which nickel is being used over here? Now, isn't nitrate a -1 charge? If there's 3 nitrates at -1, then we must have been using the nickel 3+. That's how I figure this out. So this is the +3 version of nickel. Okay. Now how does that fill with SO3? SO3 is sulfite. What is the charge on sulfite? -2. Shoot, these don't fit, hey? Because one's a +3 and one's a -2. So hopefully you've experienced this before. We're going to need to have 2 things that are +3. That makes 6. And we'll put this guy in a bracket, and we'll have 3 of those. Because 3 minus 2's is -6, and +3 and 2 is +6. And the last thing I got to figure out is what sulfite does. Yeah. Because we only put Roman numerals in when we like write it out in words like this. So if we write it in words, absolutely, we'd say nickel 2 sulfite. Yeah. But like, there's no spot for a Roman numeral in like this format here. Does that make sense? Good question. Very good question. Okay, last thing we got to do is we got to figure out what state of matter it is. So I'm running out of room in the corner here, but remember again that little table there that, you know, top one is aqueous, bottom one's solid. We got to find the table that has the SO3 ion in it, which looks like it's the last one. And it looks like sulfite is soluble with anything in group 1 or NH4+. Is nickel in group 1? No. Is it NH4 plus? No, it's nickel. So I guess it's solid. Okay, last step. Gotta balance this thing. Sometimes for balancing, you just gotta start somewhere. Like, I'm gonna start with this nitrate right here. This nitrate, there are 3 of. Over here, I see 1 of them. Okay, so let's put a 3 here. Now I have 3 sodiums. There's 2 over here. Ah, shoot. 3 and 2. That's always like, it's always the same problem with 3 and 2, right? If you have 3 and 2, what you have to do is you have to make this guy 6 by going 3 groups of 2. And I'll have to go back to this guy over here while that eraser is way too big. There we go. Pull that out. I might as well get rid of the charges while I'm at it. Clean that up a little bit. So where was I? 3 groups of 2 makes 6. I'll have to just make this guy a 6 now, I guess. Let me go back and fix that one then. Remember how like I only wanted 3 nitrates? Remember how over here I wanted 3 nitrates only? Which is why I originally put the 3 there. But now I have 6 nitrates. So if I want 6 nitrates here, I better put a 2 there and double that one. I have good news though. You know how there's now 2 nickels right here? Check this out. There's 2 nickels right here. That's good news. And there's 3 sulfites right here. Well, now there's 3 sulfites right there. Is that a question, Andrew? Oh, you're searching. Okay. That is probably the toughest thing we do in this course. That particular question right there. The double replacement with crazy charges and crazy balancing and looking things up on the table. Like, in this course, I don't think it really gets tougher than that. So. All right, let me keep moving here a little bit. I'm going to go a little faster if that's okay. We have zinc and sulfur, but I gave them in words. We need to actually put these into like letters. So zinc is Zn. The zinc comes in groups of 1, and it's solid. And we did sulfur earlier today, didn't we? Sulfur comes in groups of 8, and it's also solid. What kind of reaction is taking place here? You have an element and an element. Composition, yeah. It's going to form a compound. It's going to form zinc and sulfur together. Think of their charges. Zinc is +2. Sulfur is -2. They fit perfectly. We do need to look up its solid aqueousness. Looks like according to this table here, it's a solid, if I'm reading the table right. Because sulfur 2 negative, most things are in the bottom column. Last step, we need to balance. Zinc is balanced right off the bat. There's 8 of these guys here. There's 1 there. I'll throw an 8 there. That solves the sulfur problem. 8 sulfur, 8 sulfur. And 8 zinc. 8 zinc right there solves our problem. Once you get better at it, like you can speed things up. I've been going really slow at first. So if you're bored, I'm sorry. Okay, same thing on this next one here. We've got copper and gold 3 chlorate. Before I begin, I actually need to kind of like write out what that stuff is. So copper is Cu, and that's a solid form. And copper comes in 1s. And then gold 3 chlorate's a bit trickier. Gold is Au. Chlorate is ClO3. But the charges don't fit. Because gold is 3. What's the charge on chlorate? To go look this up. Find chlorate in your table. -1. Okay, so gold is +3. Chlorate is -1. It means we're going to need 3 of these guys to make it work. State of matter, chlorate, according to Isaiah's table, is soluble with all. Perfect. Aqueous. Makes it easy. All right. Actually, that was the easy part. We still got to figure out what it makes. All I did was just write out from here to here and here to here the words into compounds. Now I got to figure out like what's going to occur here. Well, it's the switcheroo. This metal right here and this metal right here, the gold and the copper, they're going to change places. Move this out of the way here. So we need to have copper go with the chlorate, and we need gold to go by itself. Copper is going to go with chlorate. Gold get kicked out. It's all by himself. Lonely. Oh, yeah, a couple other thoughts here. Let's start with gold. Gold's the easier one. Gold comes in groups of 1, and it's a solid. Sorry, that's kind of squished there, but that's the easier one to do. The copper and the chlorate. Chlorate has a -1 charge. Charge does copper have? Or 1. Or 1. Now, to make things simple for us in this course right here, we're going to pick the most common charge if we don't have evidence otherwise. But you guys are going to learn at a higher level of chemistry that it actually makes both versions of the copper chlorate, and like 2 reactions happen simultaneously. But like we're kind of not ready for that, so we're just going to pick the most common charge. Which one's listed first for copper? 2. Okay, so if it's the +2 charge here then, because that's most common, then we're going to need to have 2 of those chlorates over there. And I believe chlorate, I looked up on the table earlier, it was soluble everywhere, so that covers that bit. Last step. We're getting close, guys. Promise. We need to balance. And you might notice there's only one thing that's not balanced, because there's 1 copper to 1 copper, 1 gold to 1 gold, but this guy right here, there's 3 of the chlorates. Like, treat it all as one big item, hey? ClO3, there's 3 of them. And here, ClO3, there's 2 of them. How do you fix a 3 versus 2 mess? Yeah, so put a 3 here to make 6, and put a 2 here to make 6. And then you just gotta fix the other ones then. So now there's 2 individual golds that better be over here, and 3 individual coppers over there. That one's also pretty tough. Like that's also pretty high on the list of like challenging things to do. Okay, last one. Sorry that it's getting kind of squishy on this page here. I really should have made more room. Hopefully you guys can still follow. The last one here is combustion. It's actually, this was literally on a slide we had earlier. And so maybe in the interest of time, why don't I just find this on a previous slide? Okay, this is C6H14 plus O2. I believe I had it back here. Combustion, ooh, that's the smaller eraser. Let's take the bigger one. Combustion always involves some sort of hydrogen and carbon mixture and oxygen, and it always makes carbon dioxide and water. Balancing this one was kind of a pain in the butt, which is why I thought maybe I'd just show you what the answer was here. Let's just confirm the work there, right? 2 6s for carbon makes 12, and that's why there's 12 carbons right here. 2 groups of 14 hydrogen makes 28. Well, that's the exact same as 14 groups of 2. That's also 28. Then for oxygen, I'm going to start on the product side. There's 12 by 2 for oxygen. That's 24. And here there's 14 groups of 1, which is 14 more. If I add all that together, I've got 38. Well, what's 19 times 2? There we go. So since this one was already kind of done for us earlier, if you want to, you can maybe just go back in your notes and copy that one out from there. Okay? But hydrocarbon combustion is kind of nice because it always makes the same final 2 products. However, balancing combustion equations is sometimes a pain in the, So sometimes balancing these ones sucks. Okay, I have been talking now, according to my timer, there 58 minutes, which is a long time. So first of all, thank you guys for being patient. This is probably the longest lesson we're going to do, maybe all year. So why don't I pause the video now?